Hello everyone, my name is M.N. Satyanarayan. I'm a professor in the physics department of NITK Surathkal. On behalf of my department, I welcome each one of you to this course on physics laboratory. This course consists of about 7 experiments, and one of those experiments is Newton's rings, which I will be discussing. My other colleagues will discuss the other experiments in this course. Now, every experiment has a certain aim or objective. As far as this experiment is concerned, the objective of the experiment is to determine the radius of curvature of a plano-convex lens from Newton's rings experiment. Before we proceed further, I want all of you to look at these two YouTube videos which explain to you the details of this experiment. Video 1 familiarizes you with the experimental setup, whereas video 2 tells you how does one make the measurements in this experiment and what are the associated precautions. So let us start with very basics. All of you are familiar with optics. You might have learned this in school. Optics is essentially the science of light, the light-matter interaction. Optics can be classified into two very broad areas: geometrical or ray optics, and the other classification is the wave optics. You must understand very clearly when are these two regimes applicable. Geometrical optics is something that you have familiarity with in your school when you learned about lenses, mirrors, apertures, and so on. In all these discussions, you might have noticed that light has been depicted as a ray directed in a particular direction. This is an approximation, and it is valid when the wavelength of light is very small compared to the size of the objects with which the light interacts. So if you take the example of a mirror or a lens or an aperture, the macroscopic dimensions of these objects are many orders larger than the wavelength of light, which is normally on the order of micrometers. So when you're in this regime, geometrical or ray optics is perfectly valid. But when the objects have dimensions which are comparable in size to the wavelength of light, then you can no longer work in geometrical optics. You have to invoke the concepts of wave optics, and so these are two contrasting classification of optics, and we must be aware of which classification applies in which situation. I have a small portion which reviews the concepts of interference of waves which you have studied in your class 12 physics. Two waves of same amplitude, frequency, and wavelength which travel in the same direction result in superposition of these two waves. Suppose I have one of the waves given by capital A sine kx minus omega t, and another wave given by A sine kx minus omega t plus phi, where k is the wave number of the wave, omega is the angular frequency of the wave, and capital A is the amplitude of the wave, and phi is a quantity which is called as the phase of the wave. If you add these two waves, suppose then the resulting wave is something like this. So you have a wave which is given by 2a cos phi by 2 sine kx minus omega t plus phi by 2. Now two very interesting situations arise out of this depending on the value of phi. If phi is 0 degrees, then the resulting wave has twice the amplitude of the interfering waves, and this situation is called as the constructive interference. You can observe that if you put phi equal to 0 in this equation, then you have a wave given by 2a sine kx minus omega t. So the resulting wave has amplitude 2a compared to the amplitude of the interfering waves, which was only a. The other case is when phi is equal to 180 degrees. When this happens, if you put the value of phi over here, you will notice that the plus sign over here becomes a minus sign, and the two waves essentially cancel each other. This is called as destructive interference. So the constructive interference and destructive interference are the consequence of superposition of two waves which are traveling in the same direction and have same amplitude, same frequency, and same wavelength. Now the interference is essentially a redistribution of energy. Remember that energy in physics is a conserved quantity, and so in a destructive interference there is no energy. So the question is, where does this energy disappear? This energy cannot disappear. This energy has been reappropriated into the constructive interference, and therefore the interference phenomena is nothing but manifestation of energy conservation. I'm sure you all are familiar with this setup. This is the famous double slit experiment due to Thomas Young. Thomas Young lived during this period, 1773 to 1829, and he came up with this experiment in 1801, which is very popularly known as the double slit experiment. Now in this experiment, you basically have a monochromatic source of light illuminating a pair of slits S1 and S2. S1 and S2 then act as virtual sources, and the wavefronts emanating from S1 and S2 would interfere and produce an interference pattern depending on their relative phases. Now it is important that S1 and S2 are coherent virtual sources. If you have incoherent sources of light in the same physical area, then in principle you will not observe interference. Or even if interference fringes do happen, they may occur for an extremely short period of time and so may not be visible to the human eye. So it's very important to have coherent sources. So if you have sources like a laser, it's very easy to observe interference with lasers because it's a coherent source of light. So if any fluctuations happen in this monochromatic source of light, it is equally applicable to these virtual sources, and therefore these two sources always behave as coherent sources, and therefore the interference between these two sources gives rise to an interference pattern which you observe on a screen placed at a certain distance from this pair of slits. On the right hand side is a beautiful illustration of ripples in water tank, which is produced. You have a source of vibration over here, you have a source of vibration over here. Each of those source of vibrations produce ripples in the water, and those ripples will either constructively or destructively interfere depending on their relative phases. So this is the underlying principle behind any phenomena of interference. Now I take you to the experimental setup that we will be using in this experiment. This is actually discussed in video 1, and if you see these 2 videos before you start looking at the slides, then it will be much more illustrative to all of you. So this is the instrument which is called as a traveling microscope, and I have explained in my video why it is called a traveling microscope. You have an assembly that contains a plano-convex lens kept on top of a glass plate. There is a monochromatic source of light, the sodium vapor lamp. Sodium, for all practical purposes, is considered as a monochromatic source of light, but if you strictly look at its spectrum, it consists of a doublet, and I have explained in my video as to what are the 2 energy levels from where you have a doublet radiation. So you have one wavelength at 5890 angstroms and the other wavelength at 5896 angstroms. The 2 wavelengths are apart by about 6 angstroms. So the light from sodium vapor lamp falls on a glass plate which is inclined at an angle of 45 degrees. The purpose of this glass plate is to direct the light beam to this assembly of plano-convex lens and glass plate. So you have reflections from the curved surface of the plano-convex lens and the top surface of the glass plate. The 2 reflections would interfere to produce an interference pattern which is visible using the traveling microscope. The interference pattern in this case are circular and not straight interference pattern, unlike what you would see in Young's double slit experiment. The reason is that all those points which are in the same phase lie on the loci of a circle. Because of the geometry of this problem, the fringes are circular in nature. So you will have circular alternate dark and bright fringes in this experiment. Okay. Before we proceed any further, we need to look at a little bit of underlying theory of the Newton's rings experiment. This is a small schematic of the plano-convex lens that you saw in the previous slide, kept on top of a glass plate, which is this one, and this is enclosing a thin film of air between them. Now this circle is an extension drawn out of this plano-convex lens. The circle has a radius of capital R, which is the same as the radius of curvature of this plano-convex lens. And we're looking at 2 chords given by AB and EG. Okay, we have 2 chords over here, AB and EG. EG also happens to be the diameter of the circle. Now we apply the law of chords of a circle, which states that when 2 chords of a circle intersect, the product of the length of the line segments in each chord is equal. This means that AC multiplied by CB should be equal to EC multiplied by CG. Okay. From our construction, you notice that AC is equal to CB equal to R, both are equal to R. BF is same as CE, is same as AD, which is equal to T. BF also represents the thickness of the air film at the point B and F. Notice that as you travel from the exterior of the plano-convex lens towards the point of contact, the thickness of the air film progressively reduces. Okay, so this T is the thickness of the film at a particular point between the plano-convex lens and the glass plate. So if you look at this theorem of chords, you have R into R, which is R square, equals EC into CG. EC is T, CG is 2r minus t. Okay, so r square is t times 2 capital R minus t. Now if you open up this bracket, you get 2RT minus t square. Now t is the thickness of the air film, which is extremely small, and therefore you can also you can neglect the square term, leaving you with an approximated expression of r square approximately equal to 2 capital RT. Okay. Once again, we go back to our class 12 physics and we look at the phenomena of thin film interference. Now let us look at the figure that is shown over here. You have a thin film of thickness d units. The film has refractive index N2, and on the top of the film is air with refractive index N1. You have an incident light beam falling on the thin film at an angle θ1 with respect to the vertical. The light beam gets reflected at the same angle as θ1. A part of the light beam also refracts and travels to the bottom surface of this thin film. So angle θ2 is the angle between the refracted beam and the vertical at the bottom surface of this film. The light beam at the bottom gets reflected and emerges out of the film, and then the interference should happen between these two beams of light. Now, the path difference between the two reflected components of light is given by AD, and if you recall your class 12 physics, is given by 2 times N2 times T cos θ2. Of course, in our discussion, T has been the thickness of the air film. So the two reflections from the top surface and from the bottom surface of the film would have a path difference of 2 into T cos θ2. Now let us look at the figure on the right hand side. So you have a planoconvex lens, as we have been discussing, kept on top of a glass plate, and then you have an incident beam of light falling on this assembly. There is one reflection from the curved surface of the planoconvex lens, which I have marked as beam number 1, and a part of this beam also travels to the bottom glass plate and gets reflected from the top surface of the bottom glass plate, and this reflection is marked as beam 2. Now we must expect interference between beam 1 and beam 2. Of course, in our experiment, the light ray is falling vertically onto this assembly, and so light rays would get reflected from the curved surface as well as from the top surface of this glass plate, and those reflected light rays would interfere to produce an interference pattern. Now here, notice that when you have light traveling vertically down towards this assembly, the light that propagates in the region between the glass plate and the planoconvex lens travels a distance of 2t, plus additionally it also suffers a path difference of lambda by 2 with respect to the light beam that is reflecting from the curved surface. The additional path difference basically comes from the fact that light wave is propagating from a rarer medium here and getting reflected at the interface of a rarer medium and a denser medium. So if you look at basic physics, you must expect a phase change of pi or a path difference of lambda by 2. So the total path difference between the two beams is 2t plus lambda by 2, and this path difference must be equal to n times lambda in order to satisfy the condition for constructed interference.
Now if you substitute for d from equation 3, and if you realize that since the fringes are circular in nature, the radius of a given fringe is equal to r, which is equal to capital D by 2, where capital D is diameter of a given fringe. Once you realize this, from equation 3, it's easy to see that for any two rings n and n, okay, the mth fringe and the nth fringe, I can always write this equation from equation 3. Okay, so I have dn square by 4 capital R equal to n minus half lambda, and dn square divided by 4 capital R equal to m minus half lambda. And if I subtract this quantity from this quantity, I'll get dm square minus dn square divided by 4 capital R, which is equal to m minus n times lambda. So this expression enables us to find out the radius of curvature of a plano-convex lens once you measure the difference of the squares of the diameter of any two rings m and n. And if you have the knowledge of the wavelength of light, then it's easy to calculate the value of R from this expression. So this is the tabular column that you will be filling for the experiment. So the first entry that you will make in this tabular column is the least count of the apparatus, the least count of the traveling microscope. And I have discussed this in video 1 as to how to determine the least count of the traveling microscope. And then you have to position the crosswires of the telescope on the 18th ring on the right side. Video 2 tells you how do you count the rings and how do you position the crosswire on the 18th ring. So you find out what is the pitch scale reading, what is the head scale reading, and then calculate what R2 is. Now R2 will be equal to the pitch scale reading plus the head scale reading into the least count. Okay, so that gives you the value of R2. Move from 18th ring to 14th ring. In positioning the crosswires of the telescope on a given ring, please make sure that the vertical part of the crosswire becomes a tangent to a given ring. So find out the position of 14th ring, find out the position of 10th ring, find out the position of 6th ring on the right side. Now travel across the center of the rings, go to the left side and continue taking the readings of 6th ring, 10th ring, 14th ring and 18th ring. Now once you have R2 and R1 readings, you are in a position to calculate the capital D, which is R2 minus R1. And once you do this calculation, you can also calculate what is capital D squared. All along you must have the units. These are very important in physics. You must have appropriate units all the time with a quantity that is calculated. So you can fill in this column, which is D squared. Now you need to fill this table as well, which gives you the difference between the squares of the diameter of nth ring and nth ring. Now if I choose my nth ring and nth ring in such a way that n minus n is 4, then I can always find the difference dm square minus dn square. So for the first entry over here, this is essentially d18 square minus d14 square. For the second entry over here, it is d14 square minus d10 square. And for the third entry over here, it is d10 square minus d6 square. So you can fill up this table, and a look at this table will tell you whether there is any sense in going forward, because if these values are not consistent, if they are very random, then obviously you have made some kind of error in taking the readings. If you've done everything fine, then these readings should be very close to each other. And then you find the average dm square minus dn square. By adding up these three readings and dividing by 3, you get the average. And then substitute the average value of dm square minus dn square in the numerator of this expression. Denominator, you have 4 times lambda times m minus n, and because we have chosen n and n to be such that m minus n is 4, you need to substitute 4 over here. And once you do the calculation, you have the radius of curvature of the plano-convex lens determined from this formula. But the job is only half done. You also have to plot a graph between d square and the fringe number. Okay, so you plot d square on the y-axis, the fringe number on the x-axis, and once you do this, you're in the position to plot the graph. And once you plot the graph, it is also possible to find out the slope of the line. And once you have the knowledge of the slope from the graph, you can always calculate the radius of curvature of the plano-convex lens, this time from the graph. Now at this point, I would have expected you all to have watched the 2 videos, and if you have not, please do, so that we can proceed further and look at more details of the calculation. Now, assuming that you have seen those videos, I'm going to go to the next slide. So this is how a filled table of the experiment looks like. The first line of this page is the least count, which you must record in your lab record book. The least count has been determined as I explained in the first video, and it is 0.01 millimeters, which is also equal to 0.001 centimeters. And I have taken the reading of the 18th ring by positioning the crosswires of the telescope, the vertical crosswire of the telescope, and in positioning it, I have ensured that the crosswire is essentially a tangent to a given ring. So I take the reading of the 18th ring and move very carefully to the 14th ring, ensuring that I don't miss my count. And I take the reading of the 14th ring, 10th ring, 6th ring, go across the center and take the reading of the 6th ring, 10th ring, 14th ring and 18th ring. And then I can calculate d, which is r2 minus r1, fill up this column, and also calculate d squared and fill up this column. And please note that you must always have the appropriate units always mentioned along with the values. Once you calculate the d square column, it's also easy to calculate the dm square minus dn square. So the 18th ring minus 14th ring of this value, 14th ring and 10th ring of this value, and 10th ring and 6th ring of this value. Okay, so that's how you get. You notice that these values are extremely close, they are not random, and so I know that I have done the experiment correctly, and so I can proceed further. So all you have to do is average out these values. So the average dm square minus dn square is listed below. Plug it in this expression with m minus n equal to 4, and you'll get a value of 66.49 centimeters. It is important that though the wavelength of the sodium vapor lamp is given as, the sodium vapor light is given as in angstroms, you must convert that to centimeters, because the numerator is also in centimeters. Okay, so that you can cancel out easily. So you get an answer of 66.49 centimeters. Now the job is only half done. The remaining job is to plot the graph, and the graph is plotted by plotting these values on the y-axis and these values on the x-axis, and from the graph one can determine the slope and plug in the value of slope in this expression to obtain the radius of curvature of the plano-convex lens graphically. Now you could use any of the softwares which are available. You could, if you're comfortable with Microsoft Excel, you could use that. Or if you want to use MicroCAD Origin, if you have access to it, you could use that as well. If you have neither of these, you still do not have to worry. There are plenty of websites that will plot the graph for you. All you have to do is to key in the x value and y value, and you have the graph on the screen, which you can download and use for your calculations. However, in this experiment, I have used Microsoft Excel to plot the graph. Now this is the graph of the square of diameter of the dark fringes versus the fringe number. As you can see, the title of the graph. All the graphs that you plot in this course must have a title. Okay. On the x-axis, I have plotted the ring number. On the y-axis, I have plotted the diameter square of all the rings along with the units. And when you plot the data points, you get a graph that looks like this. So you have a data point over here, over here, over here, and over here. Now you need to fit a trend line, and Microsoft Excel has a feature by which you can add a trend line to a given graph. This is also called as line of best fit. And once you have this line, you can also ask the software to write out the equation that describes this line. Now you notice that this equation is of the form y equal to mx plus c, where m is the slope of a line, and you can read off the slope of a line from this equation. So this slope is 0.0159 centimeters square. Okay. The inset here shows the worksheet wherein I've keyed in the x values in column A and y values in column. Okay, and it's easy to plot a graph like this. You must also have the title on the x-axis along with the units if applicable, and title on the y-axis along with the units, and you must also mention the scale that you have used for the graph. This is very important because we need to maximize the plotted area of the graph in order to get an appropriate slope for the calculation. So here I have chosen a scale where one major axis on the x, one major tick on the x-axis corresponds to 2 rings, and one major tick on the y-axis corresponds to 0.05 centimeters square. Okay, so on this graph, you must only mention the slope value, and all rest of the calculations must be done elsewhere. So from the value that I obtained for the slope of this graph, I can go back to the expression to calculate the radius of curvature graphically, and so when I plug in the values, I get an answer of 67.45 centimeters. Now it's also important to calculate the percentage error between the calculated and the graphical values. So this is the formula I have used to calculate the difference between the graphical value and the calculated value. It turns out to be 1.4%. Now, apart from doing this experiment and determining the percentage error between the graphical values and calculated values, it is equally important to understand the sources of them. The first and the most important error that can come in the experiment is the backlash error. I have explained this in the first video. In the experiment, you're essentially using a micrometer screw, and we all know that if you traverse forward and backward in a micrometer screw, you can introduce what is called as a backlash error. So you must avoid going back and forth when you're making the measurement, which is always useful to make the measurement only in one direction. So you move from right to left or left to right, but do not go back and forth, otherwise you will inadvertently introduce backlash error. Focusing on the fringes is absolutely important. You must ensure that you adjust the vertical column of the traveling microscope to obtain a very sharp image of the fringe in the field of view. Okay? And equally important is the fringe visibility. You must ensure that the fringes are maximally visible, which can be done by adjusting the experimental setup a little bit this way or that way while watching through the eyepiece. Okay, so you stop at a point where you feel that the fringes are extremely well discernible. The bright fringe must look really bright and a dark fringe must look really black, okay, or as dark as possible. All of you must have studied in class 12 that visibility of a fringe is given by I max minus I min divided by I max plus I min. Visibility of the fringes will be 0 if I max and I min are one and the same, in which case the fringes will not be distinguished. Okay. On the other hand, you can maximize the visibility by really making the bright fringe very bright and the intensity of the dark fringe can be made very dark so that the visibility is as close to 1 as possible. So these two things are absolutely important and you must do these things before you start taking any measurement. A third thing that can contribute to the source of error is inability to get a sharp image of the crosswires in the field of view. Now this can sometimes happen in your experimental setup if the crosswires get slightly dislodged from their actual positions. If you observe that the crosswires are not getting focused, you must alert one of our lab staff to come and fix it for you. Okay. Otherwise, if you have a blurred image of the crosswires, you will not know where exactly you're placing the crosswires to take the readings, and you can have error creeping into your experiment. Missed rings can always happen, especially if you're not very careful while observing rings at the extremes, which are very closely spaced. So ring number 18, 14, 10 are extremely closely spaced, and when you take the readings of these rings, you must be very careful. When you start moving a micrometer screw, you must not remove your eyes from the eyepiece. You must keep track of how many fringes are crossing the crosswire and stop at the appropriate fringe. Okay? Otherwise, missed rings can actually cause a big error in your experimental value. Calculation errors can always creep in. This is completely in your control. Please make sure that no calculation errors creep in your results. If you're plotting a graph in a graph sheet, as you would probably do in the lab, if you do not have access to the computer, then the procedure used to obtain the best fit line can affect the percentage error. Now, if you're drawing manually the best fit line, the best way to do that is to put your scale in such a way that you are able to see the points above the scale and below the scale, and then orient the scale in such a way that you can average those points easily, and the number of points above and below the scale are roughly equal. Then you draw the line, which will then be the best fit line approximately. Now that's the best you can do when you're doing it manually. The best way to do that would be to get onto a computer, get onto a software that can do the best fit analysis for you. So if you keep in mind these 6 sources of error, then you can minimize this percentage error between the value that you calculate from the formula and the value that you calculate from the graph. So I hope this description of the experiment makes you feel comfortable doing the experiment, and more importantly, you must also enjoy doing the experiment rather than doing it manually. You must also enjoy doing the experiment, and if you do that, I'm sure you will get a very good agreement between the calculated value and the plotted value.
Okay, let me now familiarize you with the equipment that you're going to use for Newton's rings. Here you see a large wooden box. Now this wooden box houses a sodium vapor lamp. If you can see inside, there's a glass tube, okay, which is filled with sodium vapor. It's essentially an electrical discharge tube. This is the power supply which is used to power up the sodium vapor lamp, and very soon we'll turn it on. Okay. Now what is special about sodium vapor lamp is that it is nearly a monochromatic source of light. Now your physics course will tell you that ideal monochromatic sources of light don't exist in nature because of the uncertainty principle. So we can consider the practical sources of light to be nearly monochromatic, but not exactly monochromatic. So in the sense that there will be some spread in the spectral lines of these sources. So if you look into the electronic configuration of sodium and look at the energy levels of sodium, there is a 3p level and then there's a 3s level. Okay, the 3p level is actually split into two sub levels. You have 3p 3 by 2 and 3p half, and because of the split in the 3p level, the de-excitation of sodium atom from 3p to 3s gives rise to two very prominent spectral lines. Now these two spectral lines are apart by about 6 angstroms in wavelength. Okay, so you have 5890 angstroms and 5896 angstroms. So it's called as a sodium doublet, and it's very famous. You can Google up the sodium doublet on your Google Chrome and you can learn more about it. Okay, so this is the light source we're going to use, and for all practical purposes you can consider this to be a monochromatic source of light. What else are you going to use is this piece of equipment, which is called as the traveling microscope. The traveling microscope, it's called so because there is a XY stage. Okay, so let me just try and tell you, this circular scale that you see over here, it translates the stage in this direction, the horizontal direction, and there's another scale which you see over here. Okay, and if you turn this knob, this stage will move in the vertical direction. So you can actually travel in the XY plane by manipulating these two circular stages. Okay, circular screws. Now this is the reason why it is called a traveling microscope. Okay, now this is the setup that you have, and somewhere over here, if you see this assembly over here, this is where at the bottom over here, this is where you have the plano-convex lens, which is kept on top of a glass plate. You have another glass plate over here, which is at about 45 degrees with respect to the vertical, and that is basically to direct the light coming from the sodium vapor lamp into the assembly over here, which contains the plano-convex lens and the glass plate. Now this thing which you see over here, this is called as the objective. Okay, and it carries a crosswire, and top over here what you see is called as the eyepiece. Okay, and you see a number on that which says 10x, which means that the eyepiece offers you 10x magnification. Okay, this first thing that you have to learn when you're using a traveling microscope is to learn and calculate its least count. Okay, now the formula for least count is the pitch divided by the total number of divisions on the circular scale. Now this is called as a circular scale. In your lab manual, this is also called as a head scale, and over here you see this is the pitch scale. Okay, now if you just look at this scale, this looks very similar to your normal scale that all of us use. Okay, if you look at a usual scale that all of us use, you will notice that the smallest division in such a scale is 1 millimeter. Okay, now the question is, if I have an object whose dimensions are less than 1 millimeter, can I use the normal scale? The answer is no, because the normal scale minimum it can measure is 1 millimeter. Okay, so if I have to measure something which is smaller than 1 millimeter, I need a scale with much higher resolution. So if I just had only this part in my equipment, then I would not have been in a position to measure smaller dimensions using this apparatus. So this is why a circular scale is added. So this is the head scale or circular scale. Let's try to find out how many divisions are there in this circular scale. So this is, you notice here is a 0 over here, and that coincides with a 0 on the circular scale. I'm going to turn it. Okay, so that's 10, 20, 30, 40, 50, 60, 70, 80, 90, and that's 0, 0 again. Okay, so there are 100 divisions. Okay, 90 and then back to 0. A 0 is same as 100. So there are 100 divisions on the circular scale, and let's bring it back to 0. 60, 50, 40. Okay, so that's 0 again. Okay, so your pitch scale is also showing 0, 0. Okay, so this is the pitch. Now I call this as a pitch scale. Okay, let's try to find out how much distance the pitch travels, the main scale travels for one complete rotation on the circular scale or the head scale. Okay, and that will tell us what is the pitch of the pitch scale. So notice it is 0, 0 right now, and this is also 0, 0. So I'm going to start turning this knob through one complete rotation. 90 and 100. Okay, so I've given one complete rotation, and this is exactly traveled 1 millimeter. Okay, so the least count is pitch divided by the total number of divisions on head scale. Pitch is the distance moved by the main scale in one complete rotation of the circular scale. In one complete rotation of a circular scale, the main scale has traveled 1 millimeter, and therefore the pitch is 1 millimeter. Okay, and therefore the least count of this apparatus is 1 millimeter divided by 100, because there are 100 divisions on the circular scale. Okay, so that is 0.01 millimeter, and so that is 0.001 centimeter. Okay, so if you want to measure something which is smaller than 1 millimeter, you cannot do with this scale alone, the pitch scale alone. You need to have the circular scale as well. So there are a few things I want to tell you. Supposing I have advanced further, and now you see as I go further, the 0 on the upper portion coincides with, let me just move a little more. Okay, now you notice that the 0 on the upper portion is somewhere in between the first and the second marking. Okay, that is between 1 millimeter and 2 millimeter. Now, can you say it is 1.5? No, I don't think that's correct, because the pitch scale can read only up to 1 millimeter, so you can't have a fractional value over here. So the question is, you have come away from 1 millimeter, but you have not yet reached 2 millimeters. So where are you exactly? Now where are you exactly is exactly told by the circular scale, which is over here. Okay, so the circular scale is reading that is 45, 46, 47. 47th division is coinciding with 0. Okay, notice that below is 50, above is 40, and so if you count from there, you will see that this is the 47th division that is coinciding with 0. So you have crossed 1 millimeter, but you have not yet reached 2 millimeters. So your reading will be pitch scale reading plus head scale reading into least count. So pitch scale reading is 1 millimeter. Okay, you have not yet come to 2 millimeters. So you have crossed 1 millimeter, so it's 1 millimeter plus head scale reading, which is 47, into 0.01 millimeter. Okay, 47 into 0.01 is 0.47 millimeters. Okay, so 1.47 is the actual answer. So 1 plus 1 millimeter plus 0.47 millimeters, it's 1.47. Okay, so if I did not have the circular scale, I would not have been able to find out what is the reading when the 0 on the top portion is somewhere in between the 1 millimeter marking and 2 millimeter marking. Okay, so the answer now is 1.47. So that's how you read the scale. Okay, you have to note what is the 0 on top portion coinciding with in the pitch scale. You have to then note what is the reading on the head scale, and then use the formula that the total reading is PSR, the pitch scale reading, plus HSR into least count. Okay, so that's the total reading. So this is basically the setup that you're going to use. Okay, so I'm going to turn on the sodium vapor lamp now. So let's turn it on. So here's the distribution board. Turn it on. Turn on the power supply, and you see here that the sodium vapor lamp has just started. It will take some time for it to come to full intensity. So when it comes to full intensity, we will continue this video. For the moment, I am going to pause it, and then we will come back to it once the lamp has come to full intensity. Okay, so you see that the lamp is glowing, and the light that is emitted by the lamp at the moment is about a bit pinkish in color. Okay, but we should not start the experiment at this point. You should start the experiment only when the lamp has come to full intensity. So I am going to pause the video right now, and then continue once the lamp comes to full intensity. You can see the lamp is now brightly lit. Okay, you can hardly see the sodium vapor lamp, which means it's brightly lit. So now we're ready to start the experiment. What I'm going to do is I'm going to use a small attachment here to mount the mobile phone, and I'll try to show you the fringes through the mobile phone. So here's the small attachment that I have. So I'm going to fix the mobile phone on this. This attachment has a 16x eyepiece, so I have removed the eyepiece on the equipment. So you notice that the eyepiece is removed. The eyepiece is kept over there, and I'm going to use this attachment and fix it up to show you the fringes on the display. Okay, so I'm going to pause this once again and take this time to fix up the mobile phone on this attachment, put it on a traveling microscope, and try to show you the fringes. Okay, so what you see on the screen is essentially the fringes that you observe. So if you see through the naked eye, you will exactly see the same fringes. What you cannot see here are the crosswires, which unfortunately is not visible, maybe very faintly visible. If you can strain your eyes, you can probably see it. And therefore, because the crosswires are not visible on this, I cannot really do the experiment live, but I have taken the readings and I can tell you how to go about the experiment. Now what you see here is a set of concentric alternate bright and dark fringes. Okay, these fringes basically come, as I have explained in the theory, because those points on the fringe which are essentially in the same face, okay, the loci of those points lies in a circle, and therefore you see alternate dark and bright fringes. So this is what you would observe if you were to do the experiment in the lab. Okay, what are the qualitative features of these fringes? Number one, the central disc which you see in this case is bright, but obviously when the panoconvex lens is sitting on the glass plate the point of contact, you don't expect any path difference between the reflected beams. Okay, so with the phase change of pi by 2, which is phase change of lambda by path difference of lambda by 2 for the reflected light from the bottom of the plate, you should have a destructive interference, and so the central disk should be dark. Okay, but in this case you see the central disk is bright because the interference condition has been slightly disturbed. It can get slightly disturbed even if you have a small speck of dust which is sitting between the plano-convex lens and the flat glass plate. Okay, so that can alter the interference condition, and so instead of getting a dark disk, you get a bright disk over here. Nevertheless, that's not a question, that's not a reason to worry. What is important is the fringes that are visible in the field of view. The first thing you must do when you see these kind of fringes is to ensure that your focusing is proper. So how do you do that? You have to move the microscope, the vertical column up or down. So you notice it's gone off focus. This is the best focus I can get, and once again it's gone off focus. So let's set it back to the best focus. Okay. What is the second thing that I observe? The second thing you observe is that as you go away from center of these fringes to the outside, you notice that the fringe width has reduced. Okay, the fringes become thinner and thinner as you travel outward from these from the center of this fringes. Okay, now that can once again be understood from the Young's double slit experiment. If you manipulate the spacing between the two virtual sources, then you can notice that the fringe width can be actually altered. Okay, so as you're traveling from the point of contact outward, you notice that the two reflections, the separation between the two reflections is going on increasing, and so you can reason out why the fringe width should reduce as you go outward. So what does it mean for me as far as the measurement is concerned? Remember that you have to start counting the fringe number, okay, from the center onwards. So you got to be very careful in doing that fringe counting. Okay, so if you remove your eye from this experimental setup even for a minute and lose the count of fringes, then you have to start all over back. So that has to be avoided. Now how do I calculate? Now this experiment consists of calculating the diameter of the rings, okay, the dark rings. So if you see the first dark ring surrounding the central bright disk, if I place the crossfire on the right side in such a way that the crossfire, the vertical part of the crossfire is tangent to the outside portion of the ring, I can note down the main scale reading and the head scale reading. Okay, and then I go to the left hand side to place the crossfire on the left portion of the ring, okay, to the left of the center, and then one can take the pitch scale reading and head scale reading once again. Okay, in both the cases I have to ensure that the crossfire is appearing tangential to the ring. Okay, now here's a word of caution. I can take reading on the left side, I can take reading on the right side, I can take left once again, I can take right again for yet another ring, but this will give me wrong readings. The reason is, do not forget that you're using a micrometer screw here to take the readings. Okay, a screw gauge, essentially it's a screw gauge. So if you go back and forth in a screw gauge, you might have learned in your school that this introduces something called as a backlash error. Okay, and once the backlash error is introduced, your readings are going to go completely wrong and you will get a horribly wrong answer. So what is the way forward? What we do here normally is that we ensure that we do the experiment by traveling only along one direction. Okay, that is, either you go from leftmost ring to the rightmost part of the ring, or you start from the right side and go to the left side. Okay, in both the cases we ensure that we travel only in one direction and not keep changing the direction. Okay, this is to avoid the backlash error. So what do I do now is I'm going to move the circular scale Okay, so we can't count the rings because the crosswires are not visible, but then let me just do a rough counting. Okay, so this, I crossed ring number 1, 2. Okay, let me just quickly go outward. Now you see the dark and bright fringes are so closely spaced. Okay, so this calls for real care in noting down your readings, because a small error here can actually make your readings go completely wrong. Okay, so so while I'm moving this, I should also be counting the rings that cross the crosswire, and let's assume that I go to the 18th ring. Okay, for the moment let's assume that I go to the 18th ring. Let me just increase the magnification. Yeah, so this increases the magnification. You can see the rings are a little more clearly visible, but you don't have this liberty when you're doing with your naked eye, okay, because you cannot change the magnification that your eye offers. Okay, but in a digital camera or a mobile phone, I can change the magnification always. So you see the ring separation is a little more clear here because I've changed the magnification. I go back to the original magnification. You can see that the rings are extremely closely spaced as you travel outward from the center of these fringes, which means that I had to be very, very careful in taking the readings as I approach from the outside. So what do I do is, as I traverse from the center of the ring to the outside, I start counting the rings. As each of those dark rings cross the crosswire, I update my count of the ring, and then I stop at the 18th ring on the right side. Okay, I note the pitch scale reading and the head scale reading for the 18th ring, and then I move inward to the 14th ring. Okay, and once again note the pitch scale reading and the head scale reading. Now when you're moving from 18th ring to 14th ring, you have to be very careful. You have to move very slowly, ensuring that you don't miss any ring, because if you miss a ring, then obviously your readings are once again going to be wrong. Okay, so once again note down the pitch scale reading and head scale reading for 14th ring, come down to the 10th ring, do the same thing, come down to the 6th ring, do the same thing. Notice that I have come from outside to inside. Now go across the center and start taking readings of the 6th ring, the 10th ring, the 14th ring, and the 18th ring. So by doing this, I have ensured that I am traveling only in one direction. Okay, so by ensuring this, by doing this, I'm ensuring that I'm traveling only in one direction. It's not necessary that you have to come from right to left. You can also choose to go from left to right. It's completely your discretion. But what you have to observe here is that the motion of the screw should be only in one direction, not in forward and backward mode. Okay, so these are some of the things that you must keep in mind when you're actually doing the experiment. So because you cannot see the crosswires over here, the problem here is that the depth of focus of a digital camera, as you have on the mobile phone, the depth of focus is quite less. Okay, fortunately, you know, the nature has given us a beautiful depth of focus. Human eye can focus on two different spatially separated points quite easily. So when you do the experiment with naked eye, you can focus on the rings as well as the crosswire at the same time. But for some reason, this digital camera is unable to focus on both the things. So I cannot see the crosswire, but I can see the fringes. Okay, so I cannot take the readings here for this point, but then I have done the experiment with naked eye, and I can share my readings with you, and I can tell you how do you calculate the radius of curvature once we understand how to take the readings. Okay, so the readings have been, the way to take the readings is exactly the same as the first part of the video that I told you, how to read the pitch scale and how to read the circular scale. And once you understand that part, you can easily take the readings, and the rest of the calculation I will tell you. Okay, so this is how we do the experiment. And one more important thing that I want to tell you is, before you start taking any readings, one thing is to focus on the fringes well, so that you get a sharp image of the fringes. The second thing is to also ensure that the visibility of the fringes is maximum. Okay, now visibility of the fringes, as you know from your 12th class physics, is given by I max minus I min divided by I max plus I min, where I max is the intensity of the maxima and I min is the intensity of the minima. Okay, so when does the visibility become zero? When I max and I min become equal, you say visibility is zero. So you cannot distinguish between the bright fringe and the dark fringe. It all looks the same. So if you have to maximize the visibility, the bright fringe has to look really bright and the dark fringe should look really dark. Okay, and that can be done by slowly manipulating the apparatus while watching the fringes, and set it up for maximum visibility of the fringes. Okay, so once you do these two things, focusing on the fringes and then setting it up for the maximum visibility, you're all set for taking the readings. And while taking the readings, you have to ensure that you travel only in one direction and not go back and forth. Okay, as I have shown you in the video. So once again, I will stop this video over here, and then we will talk about how to calculate the radius of curvature from the observations.